So this video is strictly for AP Physics 2, AP Physics 1, Regents, don't bother. All right, so on your reference tables, you have the magnification formula, and we've already talked about that, but you also have this other equation here. And this has two names depending on what you're using it for. If you're using it for curved mirrors, it's called the mirror equation. And if you're using it with thin lenses, it's called the thin lens equation. And either way, this equation it's a little different. It's 1 over the object distance plus 1 over the image distance equals 1 over the focal length of the optical object you're using. That formula, I want to show you where it came from, at least in one instance. It's similar in other situations, but I don't want it to just be like handed down from on high. I want you to see it. So let's do a quick derivation. Let's start with a drawing. Here we have a concave mirror, and we're going to draw two principal rays off of here. The red ray is, it goes in, hits the center of the mirror, and bounces off at the same angle. We don't generally use that as a principal ray in our diagrams because it requires using a protractor in order to make sure those angles are the same, but it is true. The other one is straight through the center of curvature, hitting and bouncing straight off because it's hitting at the normal. This sets up two triangles, ABC and A prime, B prime, C prime. These triangles have an angle alpha in common. They have to be congruent, right? Those are alternate interior angles. Let's take the tangent of alpha for each one. Tangent is opposite over adjacent. So we have opposite over adjacent for ABC, and we have opposite over adjacent for A prime, B prime, C. Let's set those equal to each other. Group the opposites and the adjacents, and then use our previous formula that the ratio of heights is equal to the ratio of distances. Now we can multiply back over, multiply through the binomials. Rearrange and then divide both sides by SI, SO, R. Finally, we know that 2 times the focal length equals the radius of the circle. And there you go. There's the mirror formula. It works for diverging mirrors as well, and you can do something very similar when it comes to lenses. I'm not going to go through it again for each of those, but it does work, trust me. It makes me a little crazy that the College Board decided to put these equations in absolute values because the positives and negative signs matter a lot, and these equations break down if you don't use the right signage. For mirrors, the signage is really quite easy. Anything in front of the lens is positive, anything behind the lens is negative when it comes to your object and image distances and your focal length. For your heights and magnifications, anything positive is erect and anything negative is inverted. For lenses, it's a little different. Lenses sort of treats a converging lens as your default situation. So you get this flip of positive and negative. If you have an object and then the lens and then the image here, that's going to be positive here and positive there. Whereas if you have the object here and it's creating an image on the same side of the lens, that's going to be positive and negative. So there is a little bit of a flip when it comes to lenses, but this is what the chart looks like for your signs. Knowing these signs for mirrors or lenses and knowing the equation, either the mirror equation or thin lens equation, which looks exactly the same, you can mathematically solve for anything that you could also use a diagram to solve for. This allows you ways to double check what you're doing. The diagrams are typically nice as a quick sketch, especially for like a multiple choice question where you can just very, very quickly go through and draw things. You'll probably have to draw some diagrams on your long answer questions too. And if you know them, it's really easy. If you don't know them, it's an easy way to miss points. So make sure that you know them. But those diagrams also serve as a great check for your math. You can do the math and say, hey, I got positive, so I have an upright image, but when I drew the diagram, I ended up with something inverted. That means you probably have a sign error somewhere when you did the math, right? So you can do it to double check. And if you say, oh, well, I got negative and I ended up with a drawing that showed me that it was negative, they're both inverted, that's a sign that you probably did not make that sign error. You could use that a lot to just do a quick check on does this make sense or does it not? A final piece of information you need to know is, what about a lens that's not symmetric? What if you have a lens that's made of two different circles, like say this one? There is a formula for it right here, okay, but you don't have to memorize that. Whether this is going to converge or diverge and how much depends on the radii of the two different surfaces. You could have one that's concave and one that's convex. You could have both convex, both concave, one concave and one flat. And however that works, the general idea is that the more pronounced curve wins. So if you have one that looks like this, well, that's more concave than convex, and concave is diverging, so that's going to be a diverging lens. If you have one that looks like this, well, that's also going to be diverging. Converging lenses, you're going to have, say, this or this. The more pronounced curve wins in every case. And really, that's it for the math for lenses and mirrors. So we're going to move on to some other optics phenomena not involving lenses and mirrors, but involving some of the interesting behaviors of waves.